Pre-statistics. Using graphs and tables to solve systems. Lesson objective. Use a graphical approach to solve systems of linear equations. Lesson objective. Systems of equations. Chapter 6 covers a very important class of mathematical problems. Here you'll learn to find values of two or more variables at the same time. These problems occur frequently in business and economics as well as social and physical sciences. Intersection point of the graphs of two models. Definition. A system of linear equations in two variables, or a linear system for short, consists of two or more linear equations in two variables, normally x and y. Solution of a system. Definition. We say that an ordered pair AB is a solution of a system of two equations in two variables if it satisfies both equations. The solution set of a system is a set of all solutions of the system. We solve a system by finding its solutions. Now, for most cases with a system of linear equations, the solution will be one ordered pair. In general, the solution set of a system of two linear equations can be found by locating an intersection point or points of the graphs of two equations. Example 1. Find all the ordered pairs that satisfy both equations. Y equals 2x plus 1, y equals negative 3x plus 6. Solution. Graph each equation on the same coordinate system. So the blue line is y equals 2x plus 1. The red line is negative 3x plus 6. And the point that they have in common is 1, 3. So 1, 3 is a point that's on the blue line, and at the same time it's on the red line. For an ordered pair to be a solution, it must represent a point that lies on both lines. The intersection point 1, 3 is the only point that lies on both the lines. To verify that 1, 3 satisfies both equations algebraically, we substitute the ordered pair 1, 3 into both equations, and we should be left with true statements. So for y equals 2x plus 1, y is 3 and x is 1, we have 3 is on the left hand side. On the right hand side we have 2 times 1 plus 1. 2 times 1 is 2 plus 1 is 3. The left hand side equals the right hand side. So 1, 3 is on the line y equals 2x plus 1. To see if 1, 3 is on y equals negative 3x plus 6, we substitute the values in. So again, this time we have 3 equals negative 3 times our x, which is 1, plus 6. Following the order of operation, we have to multiply before we add, and we're left with 3 equals 3. Again, that's a true statement. So we have verified that 1, 3 is a solution to this system. Example 2. Determine whether negative 4, negative 8 is a solution to the following system. So we simply substitute negative 4, negative 8 into both equations. So for the first one, 2x minus 3y equals 16. The right hand side is 16, and if this point is on this line, this should equal 16. So we have negative 8 plus 24 equals 16. Leaves us with 16 on the left hand side. So it is on this line. To check y equals 4x plus 8, again we substitute negative 8 as y, negative 4 is our x. So now we multiply these two and add 8, and hopefully we will get negative 8. This becomes negative 16 plus 8, which is a negative 8. So we have negative 8 equals negative 8. That's a true statement. The point negative 4, negative 8 is the solution because it is a point that is on both lines, and it makes a true statement for both equations. Example 3. Determine whether 1, 5 is a solution to the following system. So we check the first equation. 5 is y and x is 1. So for the left hand side we have 10. For the right hand side, we have 3 times 1 plus 7, which gives us 10. So it checks. Check the second equation. We have 1 equals negative 10 plus 6 times our y, which is 5. So on the right hand side of the equal sign we have 20, and that does not equal the left hand side, which is 1. So because 1, 5 does not work for both equations, it is not a solution to the system. Example 4. Solve the system y equals 2x plus 4 and y equals negative x plus 1. Solution. We graph the equations. So for y equals 2x plus 4, the y-intercept's 4. Then we do our slope, 2 over 1. We go up 2 over 1, or we can go down 2 over 1. For the equation y equals negative x plus 1, the y-intercept is a positive 1, and the slope is a negative 1. So we go down 1 and to the right 1. So we rise a negative 1, we run a positive 1, or we can rise a 1 and run to the left 1, which is a negative 1. And we see that the solution is negative 1, 2. To verify that negative 1, 2 is a solution, we substitute them in to both equations. So for the first one, we have 2 equals, possibly, 2 times negative 1 plus 4. So we have 2 equals 2, and that's a true statement. For the second equation, we have 2 equals negative 1, which becomes a positive 1 plus 1 is 2. So this is a true statement. So we have verified that negative 1, 2 is a solution. We can use the intersect feature on the graphing calculator. So we hit our y equals. If you have a stat plot on, turn it off. For the first equation, for y1, type in 2x plus 4. For y2, type in negative x plus 1. Next, we want to hit second trace, which is calculate, and we're going to look for the intersect feature, which is number 5. The first thing the calculator asks is for the first curve. We pick a point on one line, we hit enter. Then next it asks for the second curve, so normally it automatically jumps to the second line. We hit enter. And then it asks for a guess, so you put your cursor close to where you think the intersection point is. You hit enter. And then it comes back and tells you that the intersection is negative 1, 2. We can double check this by using our table feature. When x is negative 1, the two y values are the same value, 2. Warning: after solving a system of two linear equations, it is a common error to check that a result satisfies only one of the two equations. It is important that you check your result that satisfies both equations. Example 5. Find the solution to the system of equations by graphing. X plus y equals negative 2. 2x minus 3y equals negative 9. First, we need to put both equations in y equals mx plus b form, or in other words, we solve for y. Then we graph each using the y-intercept and the slope. For the first one, we subtract x to both sides. We are left with y equals negative 2 minus x, or we could rewrite that as y equals negative x minus 2. For the second equation, we subtract 2x to both sides. Now we need to divide by negative 3. The negative 3 cancel for the y, and we have a negative 2 divided by negative 3, which is a positive 2/3, times x, and a negative 9 divided by negative 3 is a positive 3. So now we graph the lines. So for the first one, we go to negative 2, that's the y-intercept. We put a dot. The slope is a negative 1, so that means we go down 1, which is negative 1, and to the right 1, which is a positive 1, and we put a dot. Then we do our slope again, down 1 over 1, and we connect the dots, and we have our first line. For the second line, the y-intercept is 3, So we go to 3 on the y-axis, put a dot. The slope is a positive 2/3, so that means we rise 2, run a positive 3, put a dot. Or we could go down 2, which is negative, and to the left 3, which is negative, and negative over negative is positive. Put a dot, connect the points, and we see that the solution to the system is the point -3, 1. To check our answer, we substitute them in both equations. So for the first one, we have -3 plus 1. Does that equal -2? And it does. For the second equation, we have 2 times -3 minus 3 times 1. Does that equal -9? So we have 6 minus 3, and that's -9. So it checks. Using the graphing calculator, we can type in the first expression in y1, -x minus 2. For the second expression, 2/3 x plus 3. We can press graph and trace, or we can use the intersection feature. So we hit second trace, then intersect, and we see the calculator tells us x is -3, y is a positive 1. If we hit our table feature, we go when x is 3, we see that for both y1 and y2, y is a positive 1. Thanks for watching.